Okay, so what we're doing today is going over the types of reactions lab, and we're going to be filling in the type of reaction, the complete correct equation, and answering the questions that go with it. You should already have your observations written down. Remember that we're putting all of our skills together when we do this. We should be able to write formulas. We should be able to decide what type of reaction it is based on the reactants. We should be able to predict what those products are going to be. We're kind of learning that and practicing that today. And then, of course, we need to be able to balance the equation. And those are the skills that you're going to have for the quiz that's coming up. All of those skills kind of go hand in hand. And if you're missing one of those skills, then that's not going to go very well for you on the quiz. So please ask questions if you have them. And remember, we're recording this for those who are gone on the field trip. So for the most part, it'll just be your own classmates that hear you ask questions. Okay, so the first reaction that you did was iron and copper 2 sulfate. And it might help to start by writing out what those reactants are. So the first reactant would be written as what? Fe, just plain iron. So I'm going to go down to the complete correct equation box and just put Fe. Then we know that there's a second reactant that is copper 2 sulfate. What is the plus 2, or what does the 2 tell you up here?
The charge.
On what?
The copper.
The charge on the copper. So it tells us that this copper is plus 2. Okay, so here's my copper. What is sulfate? Yep. Check your polyatomic list.
SO4.
And sulfate is all the way at the bottom. Yep, there it is. Sulfate's right there. So SO4, and its charge is -2. So SO4, and up here I'm going to note that the charge is -2. So if we have a +2 and a -2, those balance, you just need one of each. Okay. From what we have here, we should be able to decide what type of reaction this is. So you have to look at, do we have elements, compounds, one of each? What's going on here? There's one of each. There's one element, which is the iron. There's one compound, which is the copper sulfate. So if you have one element and one compound, what type of reaction is this?
Single replacement.
Single replacement. So up here in the type of reaction, you can abbreviate if you want, single replacement. What happens in a single replacement reaction? The iron is going to come into this compound over here and replace something. How do you decide what it's going to replace? Whatever's going to have the same charge. So if the iron has a positive charge, and we know it does because it's a metal, then it has to replace the thing out of this compound that has a positive charge. So look at the charges we wrote down up here. Which thing had the positive charge? The copper. So the iron is going to come in and replace the copper. You don't have to draw these arrows unless you want to, but that's what's going to happen. The iron is going to replace the copper, and then the copper is going to get kicked out and be by itself. So on the other side of this reaction, what do I write? What's going to be by itself? Cu. Okay, let's do that first because that's the easy one. We know copper is going to be by itself. Okay, so some of you are saying, well, I don't know the charge for the iron, and you're right, you don't. From the information that I gave you on this one, you don't know the iron's charge. But I'm going to tell you in this case that it's probably what we saw in the video yesterday. It's either +3 or +2. Let's go with +2 because that'll keep it easier. Now, on the quiz on Friday, you would be given information about what that would be. Okay, so we know we have to put Fe with the SO4, and I just told you it was +2. What is the sulfate charge again? -2, so those will balance out. Can I leave those charges there?
No.
Nope, when we're done with them, we got to get rid of them. So if you're in pencil, erase them. If you're in pen, scratch them out. Okay. Last. Almost last. We need to balance this equation. So then you check. How many irons? 1. Coppers? 1. 1. Now notice how your SO4 stayed together this time. So if you want to balance it together, you can. So how many SO4s?
1.
And?
1.
All right, this one's done. We don't even have to write any numbers down because they're all 1s. Hopefully you have this observations box filled in already. And let's go and answer the question based on our observations. How do you know that the solid product is what you believe it to be? So look at your products. Copper and iron sulfate. Which of those do you suspect is the solid? The copper, because what do you know about copper? It's a metal. It's what you make pennies out of. Are pennies solid? Yeah. So copper by itself is probably the solid. How do you know from your observations that that's true? Because the color changed to what?
Brown.
What color is copper?
Brown.
Brown, kind of brownish orange. So because of the color change, the steel wool changed color. So we'll put color change to brown or brownish red. It changed to a copper color. So that's how we know that it's copper. Okay, ready for the next one?
Did it turn to actual copper then, or no?
So what happened was the copper would come out of the solution and it collects on top of the steel wool. So there's still some iron there from the steel wool, but the copper's collecting on top of it. And that's why you see it changes color.
So technically we did kind of make copper.
Yeah, you did make copper. And if you noticed, the solution also should have changed color a little bit. If you compared it to the original, a lot of times you'll be able to see that it's a lighter blue. The blue in that solution comes from the copper. So as the copper comes out of the solution and collects on the steel wool, the solution gets progressively less and less blue. It gets lighter.
It almost had like a light gray.
Okay, let's do the next one. So, magnesium and oxygen. Before we decide what type of reaction this is, let's write down the reactants. What do you write down for magnesium? Plus O2. How do you know it's O2 and not just O? Oxygen is diatomic, so it has to be O2 when it's by itself. Now look at your reactants. Do we have elements, compounds, both? 2 elements. So what kind of reaction is this? It could be synthesis. What other kind of reaction could it be? It could be combustion. How do you know for sure that it could be combustion?
Know that it is.
Because it's plus O2 right here. Anytime you see something that's plus O2, that's probably a combustion reaction. You also know that in this case, just because that's exactly what we did, right? We took the piece of magnesium and we burned it. That's what you saw with the reaction. So that's the other way that you know. Now, with this one, we're going to choose this synthesis type because that's going to help us most in trying to figure out what our product is. if the reactants looked a little bit different, so for example, if you had what's called a hydrocarbon plus oxygen. What's a hydrocarbon, by the way? What's it made out of?
Water.
No.
Well, it's a hydrocarbon.
A hydrocarbon is made out of carbon and hydrogen. So if you had a hydrocarbon plus oxygen, then you would make carbon dioxide and water. And I think it went over that in the notes that you watched, right?
Yeah.
I think so. This one is a little bit easier to figure out when you use this synthesis type. If you have two elements that are being combined together, what are you going to make? A compound. So we need to make a compound. So we need Mg, and we need O, and now we need to check our charges. O is -2, plus 2. Do those balance? Yes. Scratch them out because you're done with them. But at this point, I always have students say, but Mrs. Peterson, there's 2 oxygens on the other side. Why isn't it MgO2?
Because it's not by itself anymore, it's not diatomic.
Because it's not by itself anymore. It doesn't have to be diatomic, and the charges tell us that. +2 and -2, those both balance. So now, we're going to take care of the fact that there's 2 oxygens on the left and 1 on the right by balancing our equation. Check your magnesiums. Good. Check your oxygens. So what should I put in front of the MgO? A 2. And then a 2 over here. And a 1 with the oxygen, or you can leave it blank. Now let's answer the questions. What type of a compound, ionic or covalent, is the solid product? Well, we only have one product, so I know we're looking at this one. How do you know it's ionic? It's a metal. Magnesium is a metal. Oxygen is a nonmetal. If you have a metal and a nonmetal, then it's ionic. The next question. No, not this week. What are 2 physical characteristics of the solid product? Physical characteristics means what did it look like? Describe some things that you noticed about it. The solid product is what was left over after we burned it. It looked like ash. Okay, so we could put ashy. Is that a word? What color was it? Gray. And it says 2, so technically that's 2. Is there anything else we could add? What texture was it? Kind of like soft, powdery. Any of those would work. Okay, next one. This one, heating sodium bicarbonate. Sodium bicarbonate, what's that? Na, I know it's got sodium in it, Na.
HCO3.
And then I gotta go to this list. Where's bicarbonate? At the top. Okay, there it is, right here. HCO3, and its charge is -1. So we have HCO3. And then we check charges. Bicarbonate was a -1. What's sodium's charge? +1, so those balance. NaHCO3. Are there any other reactants? Think about the reaction that you did. This is the one with the sideways test tube. Did you put anything else in the test tube? No. So this is the only reaction that there was. and it was heated. So we could add our little symbol for heat. What type of reaction is this? How do you know it's decomposition?
Because it's just one compound.
Because there's a compound to start with, and there's only one. There's only one thing that you're starting with. That's a giveaway that it's decomposition. If you only start with one thing, that's the only thing it can be. Now, how do we decide what this is going to break up into? This is where your observations are going to come into play. So look at the observations that you wrote down. What did you see on the side of the test tube?
Condensation.
Condensation, which is water. So we know there was water. What did your split test tell you?
There's carbon dioxide.
The flame went out, so there was carbon dioxide. Now look at our compound. What's left in the compound?
Sodium.
Sodium. But if we made pure sodium metal and there was water in there, what would be going on inside the test tube? Yeah, a big explosion, fire inside the test tube. Did you see that?
Fire.
No. So there must be something else at work here. So it turns out that your third product is sodium carbonate. And if you read your directions carefully, it did tell you that in the directions that your third product was going to be sodium carbonate. All right, gotta go over here, check our charges, look for carbonate. Clear at the top. Carbonate is -2. So CO3 minus 2. All right, so that's a -2. What charge is sodium? +1. So how many sodiums do we need? 2. So we put a 2 down here. And then we get rid of our charges because we don't need them anymore. And this is our complete equation, but what haven't we done yet? We have to balance it. So if you want to, draw yourself some little blanks. Okay, check the sodiums. They're not good. So where do we put the number? 2 on the left. Okay, then we've got 2 sodiums, 2 sodiums. Let's see, there's 2 hydrogens here and 2 hydrogens here, so that's good. Then, now this carbonate kind of broke up into a couple of things over here, so we're going to have to balance carbon and oxygen separately. So check your carbons. 2 carbons, 1, 2 carbons. Check your oxygens. How many oxygens are on the left? 6. Then we've got 1 plus 2 is 3 plus 3 is 6. Oh, we're done. This one's good. Now let's answer the question. What proof do you have of the identity of each of the 2 products that are not sodium carbonate? So how did we know that we had water? We saw what?
Condensation.
Saw condensation. How did we know we had carbon dioxide? The flame went out. We did our split test and the flame went out. Okay, ready for the back. Reaction number 4, zinc and hydrochloric acid. Okay. Starting with our reactants. What's our first reactant? Zn, zinc. What's our second reactant? HCl, and it tells you that hydrochloric acid is HCl right at the top of the page here. So we have HCl. How do we know what type of reaction this is?
one compound and one element.
There's one compound and one element, so what type does it have to be? Single replacement. What happens in a single replacement? The ZN is going to go into the compound and kick something out. How do you decide what gets kicked out? The charges. Zinc's a metal, so is it going to be positive or negative? Positive. That means it's got to kick out the positive thing, which is hydrogen. Okay, so I know I'm going to get hydrogen by itself, and it should be H2 because it's diatomic. Then what's left?
The
ZnCl, and I will tell you that zinc is almost always +2, so that's almost always okay to assume. What's chlorine's charge?
minus
-1.
one.
So I need two chlorines. So ZnCl2. Scratch out the charges because we don't need them anymore. And now we have to balance the equation. Check your zincs. Good?
Yep.
Check your chlorines.
Not good.
Not good. So where should I put the 2? In front of the HCl. So put a 2 here. And then that balances your hydrogens as well. So then that one's done. All right, let's look at the questions. In what phase, in other words, solid, liquid, gas, or aqueous, is the non-gaseous product of this reaction? So which one did I just tell you that it's not? It's not a gas. So that leaves us with solid, liquid, and aqueous. So what phase is the non-gaseous product? Well, look at the 2 products we had. Which of those was the gas? Hydrogen. Hydrogen was the gas. We know that from our split test. So that leaves zinc chloride. So look at your choices. Think about what you know about ionic compounds. Is it probably a liquid? Probably not. Most ionic compounds are not liquids at room temperature, so we'll eliminate that one. Now we have another couple choices left. It could be solid, or it could be dissolved in water. It could be aqueous. Did anybody notice anything about the zinc when you threw it away? Did it look exactly the same as when you put it in there? It fizzed, but think about the actual solid zinc. It was still a solid.
But it just changed just a little bit.
How?
It kind of dissolved.
Maybe some of it dissolved, maybe. Did anybody notice a color change on the zinc when you threw it away?
Did it get darker?
It did get darker. Very good, sir. It did get darker. So this zinc chloride was a solid. And how do you know? Because there was a darker color on the zinc. And so what that tells you is that there's probably some kind of coating that's forming there. Kind of like with the copper and the steel wool. And so that's how we know that that was a solid. All right, next one.
Are the questions going to be on our test Friday?
No, your quiz Friday is going to have
Is it only equation?
balancing equations. It's going to have predicting products, so knowing what am I going to make, and it's going to have types of reactions. There's no like, how do you know this is a solid product kind of question. Those are lab questions that we're just going through. Oh, I think it's about 20 points, but some of the questions are more than 1 point. It's just the front side of a piece of paper. Okay, So next one, calcium carbonate and hydrochloric acid. So what is calcium carbonate? Well, I know there's calcium in it. And then carbonates, gotta go to the list. CO3, what is carbonate's charge? -2. So we have CaCO3, and I know carbonate's a -2, calcium's +2. So that balances, so it's just CaCO3 plus hydrochloric acid, and it tells me that is HCl. Now I can do my type of reaction. What am I starting with? Two compounds. So what type of reaction is this? Double replacement. And when you have a double replacement, what happens? Two of them switch. Now usually, in fact, pretty much always, it should be the first things. The reason that it's always the first things is because those are both positive things. You have to switch the positive things so that you make a positive and a negative together on the other side. So if we switch the two first things, calcium is now going to be with what? Chlorine. And we need to check our charges. We said calcium was +2. What's chlorine? -1. So I need Cl2. And then I got to scratch out my charges because I don't need them anymore. Okay, what else do we have? H and CO3. And I already looked up CO3. That was -2. What's H? +1. So I need H2CO3. Scratch out the charges because we're done with those. And what's left? Balance it. Check your calciums. Check your carbonates. Good. Check your hydrogens. Need a 2.
Now it's good.
And conveniently that balances the chlorine as well. Now, before we go on and answer the question here, let's do a little side note. What did your split test tell you was present here? CO2. Do you see CO2 as a product? No. But on the front of the lab, it told you, well, I guess we'll do this up here. It told you on the front of the lab that H2CO3 dissociates or breaks down into what two things? Carbon dioxide and water. So if we went back and balanced it, this would also be a correct way to write this equation. This is where the carbon dioxide comes from. This H2CO3 right here breaks down into carbon dioxide and water. Do I expect you to know that for the quiz? No, but that's why you saw the carbon dioxide in your lab results. Okay, let's answer the question. Calcium carbonate is the main component of marble statues, otherwise known as calcite. You should remember that from earth science. And many of these statues have started to rapidly disintegrate within the past 150 years. What recent environmental condition do you think is most responsible for this? What is HCl? Hydrochloric acid. Environment. Acid rain.
It's snowing March.
This is not a test question, right?
Acid rain. Okay, we got one more to do. Lead 2 nitrate. Lead is Pb. Nitrate. Get your list. Look for nitrates. Here it is. NO3. And its charge is -1. So we have NO3. Nitrate is -1. What's the charge on the lead? +2. How do you know that? Because of the Roman numeral. So what do I need? a second NO3. I have to put parentheses because I don't want 32 oxygens. Okay, what do we have next? Potassium Chromate. Oh, gotta go back to the list. Let's see, where's chromate? There it is. CrO4, -2. So CrO4. Chromate's -2. What's potassium? +1. So it has to be K2CrO4. Do we have elements, compounds, or both? Both compounds. So this is double replacement. That means that the first things have to switch. So the lead is now with the chromate. What was lead's charge before? +2. What is chromate's charge? -2. Those are good. Scratch them out. And the last thing we have, potassium goes with the nitrate. Potassium's charge is +1. Nitrate is -1. Those balance. Scratch them out. Now we got to balance the equation. Lead is good. Nitrates. Need 2 of them over here. And that also balanced what else? For the potassium, that's good now. Chromate?
Everything's good.
Everything's good. Let's answer the question. The name of the chromate ion comes from the Greek word chroma, which means color. So wherever the chromate is, that is the color. Which of the possible products do you think is the precipitate? Which one was the bright yellow solid? The one that contains the chromate. So which of these products, make sure you list the product, not a reactant, which of these products has the chromate in it? Lead chromate. This was your precipitate. We know that because chroma means color, and the precipitate was a bright yellow. All right, very good. Turn these in when you're done with them, and we will pass out the worksheet.